Hi everyone, good evening. Today, today we would like to discuss about Embark, uh, which is the application that we are using to securely outsource middle boxes to the cloud. And this presentation is being presented by Sriharsha and Pranjal. So when we talk about outsourcing to the cloud, let's take a background of why the outsourcing has to be done, or why people prefer to outsource to the cloud. So cloud services nowadays have become a vital part because people are preferring to use cloud services rather than conventional services for data management and computational when we are dealing with data management and computation, because the cloud services are more cost effective and uh, produce high performance, have high efficiency, and because of this, so people start to think like, if we can do outsourcing to the cloud for data services and computational services, why can't we do the same thing for network outs? Why can't we do the same thing to cover the network outsourcing? Because to set up a network for an organization, it is cost oriented. It costs you so much money to set up all the middle boxes such as firewalls, NATs, so that it can scramble IP addresses and proxies. So in order to set up all of this, it does cost you a lot. So people think like, oh, why should we bear the cost uh, for all of these things? Why can't we ask the other person to provide these services, namely cloud, to provide these services for a much cheaper cost compared to what it would cost us when we follow the conventional way? But while doing so, people are encountering a major problem, that is concern for the security of the data that you are sending to the cloud to perform the middle box operations for you. Because the data that you're sending to the cloud, you're putting your entire firewalls as well as proxies, so which does invoke the concern for the security. Because without being sure that your data is going to be secure, when you give the data to the cloud service provider, uh, no one would want to use the service, because the networking data that we are going to ask the cloud provider to do for us, it has to be protected at all cost. So why are we trying to? Aren't there any existing applications which deal with this kind of issue? Yes, of course there are. Outsourcing network, and why should we do with this? So, like I have discussed before, the problem with the existing infrastructure is it is not cost effective. It does cost you more, and uh, if and when because of the existing and the applications that are in place now to support the network outsourcing to the cloud, they are not mm, as secure as people like them to be. So this in turn has caused researchers and the scientists to look more closely into this issue and figure out a solution to overcome this problem, and thereby make the whole process more cost effective and more secure. And that's what we're talking about, what is to be achieved. Because like I've said, whenever people talk about converting from the conventional way to the cloud way, basically when you want to outsource your data operations, your data setup, and your computational operations and your network outsourcing to the cloud, the one major worry for the people is uh, security. So, like we have seen in the recent years, the iCloud hack, where the hackers have divulged the celebrity information to the public, and the Target security breach, where the hackers were able to get credit cards of millions of users. So these all prove that security is a must thing that an enterprise should want. And the existing infrastructure, where you can say the service is like blind box or uplong, these these are developed to facilitate the outsourcing of network traffic to the cloud. But these two services lack in the encryption department, because the encryptions that are being done on these are very restrictive, and these encryptions do not cover a whole lot of features, which we will going to discuss down the presentation. And also, we just can't encrypt everything, and if it takes a lot of time, that is also not acceptable to the customer. So we have to maintain a balance between the security that we are providing, the effectiveness of the security, as well as the performance. So if and when we see the encryption should be up to the standards, and it should also perform, uh, it should be a balance between these two. So that and how this is being achieved through Embark, that we are going to see in the next slides. So why Embark should be considered as a solution? Embark is the first system to allow an enterprise to outsource a wide range of enterprise middle boxes to a cloud provider while keeping its network traffic confidential. How the Embark is doing that, we will see it in the next slide. And middle boxes in the Embark operate directly over encrypted traffic without decrypting it. So in layman terms, we can say the middle boxes in Embark are encrypted, and these are placed in the cloud provider. So these middle boxes work with the encrypted data and do their operations without decrypting them and disclosing the information to the service provider, which the company doesn't want. Embark supports a wide range of middle boxes with practical performance. Like I said, you can't have either security or performance. You have to have both. And Embark achieves this functionality through a combination of systems and cryptographic innovations, like prefix match. Prefix match is the one innovation which that is done on Embark, which increases the performance and as well as the uh, encryption quality that is done to the data. So, how do we design Embark, or what can we say system architecture? Uh, the figure in this slide provides you the cloud-based network architecture. See, you have the middle boxes here on the internet, which is and on the internet within the cloud provider. So these are firewalls, the T-packet inspection middle boxes, HTTP header middle boxes. You have everything within the service provider, or you can say cloud provider. This is the architecture of Aplomb. Embark is similar to Aplomb regarding the architecture, but it has certain features which operate on top of the services provided by Aplomb, thereby tightening up the security issues which Aplomb doesn't do. So Embark redirects the enterprise traffic to the cloud for middle box processing, like we are seeing in this in architecture, with confidentiality protection. So you have two parties over here: the enterprise, uh, like the servers which you are seeing to your left, the routers, and then it is connected to the internet, and you have clients over here, and in between these three parties, you have a gateway, which is typically with the enterprise. The information flow will be like this: enterprise through gateway, it comes to the cloud provider, and it comes back through the gateway to client. Okay, but if you are part of the same company, if you are trying to communicate with another system which is part of the same enterprise within the same IP range, so the information flow will be like uh, enterprise gateway, cloud service provider, to the second gateway, and to the other system. Like you can see, you can see the illustrations of what we have just discussed over here. Uh, in the first diagram to my left, like in diagram A, that diagram illustrates you how the operations are done through how the Embark does operations when you are contacting to an external site. So in here, in the enterprise, you have a gateway which encrypts the traffic. You can say, so the traffic will go through gateway to the service provider where the middle box operations will be done, and then it sends the traffic back to the gateway, which in turn receives the traffic and then sends it to the external site. In Aplomb, we have an optimization over this process where the traffic will be sent to the external site without coming back to the gateway directly from service provider. Whereas Embark does not support that, because in Embark, the traffic is being encrypted. Unless until it is decrypted from the gateway, the external site cannot understand the encrypted traffic. So it so basically you're sending data which the external site cannot understand. So which makes the whole point meaningless. So that's why you do not have a setup where Embark allows you to allows the data to flow through from service provider directly to the external site. No, it has to come back to the gateway from the service provider, and then it has to go to the external site. You can say, okay, because of going back and forth between gateway and service provider, it eats away a lot of bandwidth. And how does it perform? Because the latency will be so high. But Embark has a contingency plan for that too, because Embark, compared to the Aplomb and Blindbox, also operates on this same functionality. Embark takes much lesser time, and because the latency is also very much less, and it is within the acceptance range when you compare it with the other applications, and also because of the services that are being provided. So that's why the latency and bandwidth, the differences, they are not that much. So the people has to worry when you're working for when you are talking about Embark. But Embark gives you that optimization when you're dealing within the same enterprise. If you are talking between if two systems are being if you're talking with a system, if you want to talk with a system within the same organization, Embark allows you the optimization of sending traffic from the service provider directly to the system too. And next we are talking about encryption overview, how the encryption, how the encryption basically overview of how the encryption works. So we have a gateway and service provider, like we have discussed before. Information will pass from gateway to service provider, and again from service provider to gateway, and after that and that only, the information will be sent to external site. So first, before sending the information, in here is nothing but the packets. So before starting the transfer of information between gateway and service providers, the setup has to be done wherein we have to establish certain rules, which works on the encryption of the data, so that it can be and these rules are to be set up by the gateway, and these rules are to be provided to the service provider too, because so that he can get the rules, and based on those rules, middle boxes can do the operations, sort out the traffic, and send them to the respective destinations. So what happens, and next the data encryption and data decryption. So once we have set up the rule encryption, now we will be talking about data encryption. So when a packet reaches, the data encryption works on the packet and it encrypts the packet data, and that it in turn sends that encrypted data packet to service provider. The same thing happens to the metadata too. So when the payload metadata passes through the data encryption system, it encrypts the payload metadata and sends it to the service provider, so that the middle boxes can work on that. And in the service provider, middle boxes does the job that they are supposed to do, and then send the encrypted data packets back to the gateway. where in turn they are received by the data decryption system, which decrypts the encryption and then sends the plain text packets back to the external side, thereby maintaining the uh, confidentiality or maintaining the integrity of your data. Next, as we have discussed in the previous slide, we have said packet will be encrypted. So in this slide, we will discuss about how the packet encryption works. Uh, in Embark, a key idea is to encrypt packet field by field. For example, an encrypted packet will contain a source address that is an encryption of the original packet's source address. So in plain text packet, you'll have a source address. And in the encrypted packet too, you have a source address. But the source address in the encrypted packet is the encrypted version of the original source address which we have in the plain text packet. So that's what they're saying. That's what the author is describing here. In the packet, a field by field is encrypted. And we have to ensure that the encryption has the same size as the original data. And we have to place any additional encrypted information or metadata in the options field of a packet. Embark uses, and this can be, Embark uses 3 encryption schemes to protect the privacy of each field, while allowing comparison against encrypted rules at the cloud. So this we should take into consideration. It is not enough once we do an encryption. We have to do the encryption in such a way that it allows us to compare it with the rules existing that are rules existing on the gateway, which we have set up previous to the start of the traffic, start of the gateway to service provider. So the three schemes used by Embark to protect the privacy of each field are traditional AES, which provides strong security, but it does not give you computational capabilities. The computational capabilities in here are talking about the ability to compare against the encryption rules. So if we use only traditional AES, it doesn't give us the required output. So what we're doing is we are using keyword match and prefix match. These give the computational abilities. So in the diagram in this slide, you can clearly see what we're talking about, the encryption, basically how the packet is being encrypted. So the packet originates at the client. It has a source IP 128, destination IP 28, payload is password. It goes through gateway, where in gateway it is being encrypted. So we have discussed in the previous slide where it says the encrypted packet will contain a source address, which is an encryption of original packet source address. So in this slide, you have in the red in bold letters, the source IP is 89, whereas the source IP in the original packet is 126. And the destination IP is 199. The original destination IP is 28. And the options where we have discussed in previously ensure that any additional encrypted information or metadata in the options field. So that's why you have an options field over here. Payload is of 582 characters. So that payload makes sure that the size of the encryption done on the original data is same. So how is it going? How the encrypted packet is being transmitted over the network? So first, the gateway converts the packet from IP4 to IP6 and encrypts it. Like we have discussed in the previous slide, you can see the source IP being encrypted, destination IP being encrypted, options where you have the additional information or on metadata or the encryption, and the payload. And this options field, it has the information which will help the gateway to decrypt it when this packet reaches its intended destination. So now, once it, let's see how the flow works through the network. First, the packet passes through the firewall. Like we have said, we have a rule. We have encryption rules, and we have encrypted the packet. So now the firewall will try to match the packet with the encryption rule. So when the match occurs, it allows the packet to flow through the firewall because it will determine that the packet, the suppose the packet has arrived, and it will allow the packet to pass through the firewall, and then it goes to the exfiltration detection system, wherein the exfiltration device checks for any suspicious strings in data encrypted for deep packet so it does a deep packet inspection, and when it does not find any suspicious data, suspicious strings within the packet, it allows the packet to continue to NAT. The NAT maps source IP address to a different IP address. Back at the you can see the NAT in here. You have in NAT you have 8 9 in the red and bold indicates, and you have 0 FFFFF. So it is changing the source IP from 8 9 to 0.FFFF, so that it is allowing us to maintain an security measure above and beyond what the Embark is doing. So you can see once the packet passes through NAT, the source IP has been changed to 0.FFFF. So wherein and this goes to the gateway and to the server. So and you can see in the payload section, the size is same. The same size is being maintained within the packet through the entire way that it has traveled from client to the server. And okay, once we have talked about the broader view of how the packet is being, how the packet encryption is being matched, and how it flows within the network. Now let's talk about itself is occurring. What are the schemes that we are using to make sure the encryption itself will occur, and how we are going to maintain the computational ability and as well as give the encryption, because we have to match the encrypted packet within the network to find out where the packet is supposed to be sent and is it the right packet that we are supposed to receive. So for this, there are two schemes which are being used by Embark. Those are keyword match and prefix match. Keyword match, it is self-explanatory. You can say it matches. It has a keyword and the keyword rule. So when the keyword matches with the keyword rule, the system will determine that the packet is the correct packet which has to pass through the system. So it is an effective, or you can say rudimentary way to match the encrypted packet, but it is not an effective way because it only checks whether the packet, whether the keyword matches with the encryption rule. It doesn't determine the other information. So because of this, and it has high latency, you have to match each and every packet. So because of this, keyword match is not advisable on a large scale. Now let's go to the prefix match. Prefix match is we use IP addresses. When we look at, you can see in this picture, you can see the prefix match. How the prefix match is being done is typically middle boxes perform encryption detection over prefixes or ranges of IP. Or it also we can also use port numbers to do that. So we use IP address. We use prefix matches to match the encrypted IP addresses so that we can router can determine where the packet should be sent based on the encrypted IP addresses. So we'll go into the requirements of how what the prefix match should do. The first is it should allow for the direct comparison between an encrypted value and the encrypted endpoint. And second, it has to support the NAT functionality, and
23 minutes.
Encrypted value must be deterministic within the flow. That itself, that says like it has to be within two IP1 and port 1 and IP2 and port 2. And here you have the two algorithms which are centered to the prefix match. Basically, they let you know how you encrypt prefixes and how you encrypt values. Encrypting prefixes, it means you are encrypting the range of IP addresses, like the least possible to the highest possible. Uh, and encrypting value is the value of the IP address that you want to match when the packet passes through the network. So you have the algorithms, in order to do these things. And now my partner Pranjal will talk about enterprise gateway and
Hello everyone. I'm talking about Enterprise Gateway. The gateway serves two major purposes. First of all, it serves to redirect traffic to and fro from the cloud, which is called the data encryption and decryption, and also to give the rule encryption service. Now, the point to note is that all these three services share a private key, and they have an access to the encrypting that algorithm, which is the prefix match interval map. Here is a conceptual illustration of the gateway where you can see that between the enterprise and the service provider, there is a gateway present. Now, let's talk about data encryption and decryption. It's categorized into the following: the header middle boxes. So these are the middle boxes which operate on the IP and transport headers. They always encrypt field by field. So source IP goes to an encrypted source, destination goes to encrypted destination. And how does it work is the as my partner explained, the prefix match encrypt value algorithm is actually seeds the encryption with the seeds, which is a function of the connection information, source IP, destination IP, source provider, destination provider, and we store the AES encrypted values in the header to enable decryption. Now the payload data, now the connection byte stream is encrypted with keyword match. The data elon flows is encrypted with the same key. The device must detect whether or not there exists an exact match between a rule and a connection byte stream anywhere. Now, the payload data is encrypted with AES and it is placed in the packet. Now, let's talk about HTTP headers. They are treated specially. The untokenized HTTP URI use a deterministic form of keyword match. The difference from the normal key match is that normal key match compares roles with values, whereas deterministic key match compares two values. Now, this is the only field in which we encrypt in a weaker setting, and the encrypted values are placed in the extension channel, and the decryption is as normal using the data stored. Now, the rule encryption. So we have a rule set to perform the encryption. The encryption-based algorithms are either the keyword match or the prefix match. For example, there is a firewall containing an IP prefix that can match to two prefixes. That means we have two rules present for each encrypted prefix. Now, for the keyword match, Embark supports different models. The first one is the client and the provider, both of them know the encrypted rules. The second is just the client knows the encrypted rules. And the third is that just the service provider knows the encrypted rules. Now, talking about rule updates. Now, when the client updates their rules, the service provider must be aware of it. So, in order to maintain a consistent state. So, the gateway plays a part here, which announces to the cloud that there is an update. All the middle boxes send their current states to the gateway, for which new states are generated, new encryptions are generated, and they are sent back to the middle boxes. Once all the middle boxes are updated, the gateway sends a signal to the cloud that it is about to swap in the new data. Now let's talk about middle boxes. What are middle boxes? A middle box is basically a device which performs other than normal functions of a router when it's present between the path of a source and a destination. As you can see, it's present in the between the source and the destination. Now there are header mailboxes which operate on IP and transport headers, which include firewalls, NATs, and L3, L4 load balancers. Firewalls are read-only, but NATs and L4 load balancers may rewrite IP addresses or port values. For header mailboxes, per packet operations remain unchanged for both read and write operations. For read operations, the firewall receives a set of encrypted rules from the gateway and compares them directly against the encrypted packets just as normal traffic. Now, for the write operations, mailboxes assign values from an address pool. It receives these encrypted pool values from the gateway during the rule generation phase. Now, middle boxes compute checksums as usual after the writing. Now, what are DRP middle boxes? They are basically used to block a blacklisted IP from the extensible channel. If it comes to know, it blocks it. The HTTP middle boxes are just called as the parental filters to the DPI middle boxes, and which read the URI and it drops the packets that belong to a blacklisted connection. Now, for in order to for Embark to support the web proxy, a lot of modifications are required, but nonetheless, the performance is good. Now, what are the limitations of Embark with respect to middle boxes? Embark does not support application level middle boxes. Embark does not support running arbitrary scripts of traffic on middle boxes. Embark does not support regular expressions that cannot be expanded in a certain number of keyword matches for intruder detection. So, for example, in certain steps, if we are not able to figure out the match for a regular expression, then Embark is not able to support it. So this is a table where we can see the middle boxes supported by Embark with the encryption functionality and scheme used. The first column is the name of the middle box. The second column tells us the encryption functionality used. The third column is whether it is supported or not by Embark. And as you can see, for the regular expression match, there is only a partial support. And the last column is actually the encryption scheme used, whether it is a prefix match or a keyword match. Prefix match is a special scheme developed for Embark, which has resulted into increased performances of Embark. Now let's evaluate Embark. The specifications used for evaluations are the software, which is a Berkeley extensible software switch. Server is a 16-core server with 2.6 gigahertz. RAM is 128 GB. The network hardware is 10 GB Intel compatible network card. The number of client servers are 3. The platform to deploy middle boxes is Amazon EC2. The mechanism used to calculate workload is synthetic workload generated by the packet chain. Mechanism used to implement empirical trace, M57 patents trace, and the ICTF 2010, which are both in IPv4. The DPI processing, which is based on blind box, but the experimental results are provided only where Embark has improvements over blind box. Now, let's see the enterprise performance with regards to the gateway throughput. As you can see, with one core, with comparison to a Plume, Embark is actually achieving a very high performance. It can go as high as an average as high as 9.6 gigabytes per second per core. Now, if we start scaling the cores with 4 cores and increased parallelism for the empirical traffic generated, the server is able to forward 9.7 gigabytes per second. Now let's evaluate the encryption algorithm prefix match. The prefix match stores sorted intervals. Sorry. Every packet encryption requires a binary search of intervals. Hence, as the rule set of intervals goes high, the throughput becomes low and the processing time becomes very high. And as Binary search has a penalty of log. There is a logarithmic trend to the particular curve. As you can see in the diagram, that on the x-axis are the prefix matching rules. The y-axis, the throughput has reduced and the processing time has increased. Now in the table 2, we are comparing the encryption algorithm's performance with regards to the other order preserving encryption schemes. This is a vital point in emphasizing why the encryption of Embark is so much powerful over the other order preserving and encryption schemes. We can see that for the rule set, the computational speed is almost 4 times lower. Now let's check the client performance, where we are using a baseline and the service providers used are ISP, service providing services in central office, content distribution network, traditional cloud provider. We are just finding out the round trips from the gateway, and the mean for these are respectively 60 millisecond, 4 millisecond, and 31 millisecond. Now, how does the encryption by Embark increase the amount of data that we are sending to the cloud? Because encryption is costly if we want to send large amount of data to the cloud. Now, if the enterprises uses IPv4, there is a cost from converting from v4 to v6 in a 20 byte per packet cost. If the enterprises uses IPv6, there is no such cost. If HTTP proxying is enabled, there are on average 132 bytes per request in additional encrypted data. If HTTP IDs is enabled, there is at worst a 5 overhead on all HTTP payloads. Now let's talk about middle box performance and throughput. On the left, you can see the application middle boxes and the Embark throughput as compared to the baseline throughput, and we can see that Embark is performing good, and the performance is very good, only with the exception of NAT, where the reduction is just 2.7%. Now, in figure 9, we are actually plotting the increase in concurrent connections with the time taken for every request. And as we understand that with increase in the number of concurrent connections, the time per request increases. And as you can see in the figure, that encryption has an effect on the time it takes per request, and it is on an average higher than the unencrypted proxy. Now, one significant point to note about Embark is that the Embark gateway and the cloud maintain one long-term persistent connection. Hence, the setup cost is paid only once when the gateway is initially configured. Embark also heuristically expands regular expressions in the rule sets into exact match strings. Now, these results into the following two benefits. The first is end-to-end performance improvement, where the end hosts with the normal TCP or SSL handshake take only 3 to 5 round trips, which has a time of 30 to 100 milliseconds, which is an improvement of 4 orders of magnitude. Now, the security improvements with as compared to blind box resorts to lower security level for around 32%, 33% of the rules, but Embark only does this for 11.3%. For the second rule set, the blind box resorts to lower security level for around 50% of rules, whereas Embark does it for only 20% of rules. So as you can see that it provides better security with less percentage of rules in the lower security level. Now, let's talk about why is this problem important. Why do you think is security such an important problem that Embark is solving? Yes, this is an important problem because security is everyone's concern. No organization wants to deal with, send out its confidential data which is not secure. So no company would pay. So any company would rather pay more to keep the data secure than to make it vulnerable, even when the cost for doing so would be less. So how does the author convince us regarding their solution? We feel that the author has convincingly made their point and their solution by explaining to us the importance of threats to data, by taking real life data issues, and also they provided that there is a reduction in cost and efficiency with reduction in overheads. So this is actually a more lucrative deal for the enterprises. They compared the performance with regards to existing technologies like order preserving encryption, and came out in all at top in all aspects. So it is convincing to the end user. And the paper evaluation, if we talk about, they have talked about blind box aplomb, uh, which provide middle boxes in cloud while addressing the security problem. But as compared to them, Embark has a better performance and a broader functionality. A major advantage of Embark and its highlight is its high speed and IP encryption. It provides lesser performance overheads compared to the existing applications. Blindbox cannot support equality-based operations on encrypted middle boxes such as firewalls, proxies, load balancers, NAT, and Embark supports these operations through prefix matching. Embark does not require per-user connection when initiating communication between two arbitrary endpoints within an IP range, because as we already know, the gateway and the cloud have a persistent connection. Uh, so the blind box has to initiate handshake every time a connection is needed, whereas Embark does not. It reduces in a lot of costs and time. Embark has increased deployment ability as compared to blind box. Finally, we conclude by saying that Embark solves the security problems in network traffic outsourcing with improved efficiency and performance, which were deficit in the previous implementations. Embark encrypts the traffic that reaches the cloud and enables the cloud to process it without being able to decipher and decrypt the data, which ensures the enterprise data confidentiality. And Embark supports a wide range of middle boxes such as firewalls, NATs, web proxies, load balancers, and data exfiltration systems with competitive performance. If we talk about the future scope to Embark and the areas of future research ahead of Embark or the improvements for Embark, uh, we did we understand that prefix match has a limited set of application which is designed specifically for Embark for specific rule sets, but we can make it for a wider set of scenarios and rule sets, which would definitely be an improvement and over Embark and broaden the functioning scope of Embark. Thank you very much.